Okay, dear colleagues, today is our Kharkiv chemical seminar, and our guest, Professor Jean-Pierre Sauvage. He is a chair of Institute for Advanced Study of University of Strasbourg. He graduated from National School of Chemistry of Strasbourg in 1967 and received his doctoral degree at the University Louis Pasteur in 1971. Since the beginning of the 80s, Sauvage and his group have been interested in various fields related to the molecular science, such as coordination photochemistry and solar energy conversion, carbon dioxide electrocatalytic reduction, chemical topology, multifunctional ruthenium and iridium complexes for light-induced charge separation, multifunctional porphyrin sense models for photosynthetic reactions center, as well as molecular machine prototypes. Professor Sauvage received many awards, including in 2016 Nobel Prize in Chemistry for design and synthesis of molecular machines. The merit of his group goes to a large extent to the young and less young researcher he was working with. Many of them were impressively creative and motivated. And dear Professor Sauvage, please start your lecture.
Yeah, okay, thank you, Valentin. So before I start, I would like to thank you and the Kharkiv Chemical Seminar Organization for inviting me. I must say it's a real pleasure, to talk for some colleagues and students in Ukraine. And I would like also to tell you that I completely and totally close to you, let's say. I would like to express my solidarity with you, with your colleagues, your friends, and all the people living in Ukraine. So let's start with a few definitions. Topology, as you may know, this is the science of infinitely deformable objects. It means that you can take any object, it will have some topological properties, but if you distort it, if you compress it, if you elongate it, the topological properties will not be modified. In chemical topology, this is exactly the same. Of course, it's a vision of the mind, because if you compress a molecule to a large extent, it will, of course, decompose. And the same is true if you pull on a chemical bond. At some stage, it will break up and the molecule will be destroyed. But let's say it's kind of an intellectual game. You can speak of chemical topology. And in chemical topology, bond length and angles are of no importance. Now, let's take a look at some branch of topology, which has been very exciting for mathematicians and later on for other people. This is the Nut theory. And the Nut theory, this is part of low-dimensional topology. And I just listed here a few very simple nuts. So a nut first is a closed curve. And you can see that the simplest non-trivial nut is this one, which is called traditionally the Trifold Nut. And the Trifold Nut, if you want to draw it in a sheet of paper, on your sheet of paper, you must have 3 crossings, 1, 2, 3. This is the minimum. And if you take a ring, of course, it will be very different. A simple ring, you don't need crossings. And here you have a collection of, as I said, simple nuts, very simple. Mathematicians have identified billions and billions of nuts, of course, whose complexity is such that it is basically impossible for us to apprehend the nut itself. But you can see that there are simple nuts, a little bit more complex nuts. And the first number here, the first digit, so to say, is the number of crossings which you need if you want to draw your nut in a two-dimensional space, namely on your sheet of paper. Now let's talk about links. So nuts are one part, and links are the other part. Links, they consist of two or several interlocking nuts. And again, in topology, a ring is called the trivial nut. Trivial because you have no crossings if you draw it in a plane, or some people say the unnut. For chemists, of course, if you have something like that, you will call it a ring or a cycle or a macrocycle. Now let's look at catenanes. So for mathematicians, this is known as the Hopf link, because a German mathematician, Heinz Hopf, proposed, to call it Hopf link. It is simply a set of two rings which are interlocking with one another. For chemists, of course, as you know, this is called a catenane. Now let's take a look at the history of the field. So the field of chemical topology was basically born in 1961, thanks to the work, or let's say the theoretical work, of two great scientists, Frisch and Ed Wasserman. And those two guys were working in a big company, Bell Telephone Laboratories in the US. And I think it is interesting to note that their work was purely intellectual, and there was basically no possible application. But at the time, big companies were allowing their scientists to work on basic problems, totally fundamental research problems. And so they noticed that if you have a ring, you can draw it without crossings, and you will say that it has a planar graph because you can project it in a plane and have no crossing. And you will say also that the topology of the object is trivial. Now, if you take a nutty species like this one, this is the Trifold Nut again, you need, as I said before, 3 crossings, which means that it's a non-planar graph, and thus it is topologically non-trivial of interest. Now let's move on and see what chemists have done in the field of catenanes. So catenanes are Hopf link, as I told you. Catenanes, or let's say the simplest catenane, consist of 2 interlocking ones. And such species have been discussed orally or in the literature for decades and decades and decades. But the chemists realized that these molecules were exceedingly difficult to make. And I think the first fully convincing piece of work on catenanes was published almost 60 years ago by Schill, Professor Schill in Germany, and his boss, Professor Lüttinghaus. And those two chemists, synthetic chemists, great synthetic chemists, published a paper in Angewandte Chemie in 1964, in which they were describing the synthesis of a catenane. And that was very convincing. Beautiful piece of work, which was probably greeted by the community, but the weak point was that it was a 23 individual step synthesis. So very long, very difficult. And although it was really a fantastic piece of work, nobody tried to repeat it, and nobody tried to make catenanes. So for almost 20 years, the field of catenanes and taxanes was a dormant field. Very little happened. So we had to wait for almost 20 years, as I said. And I will now explain you how we entered the field. And you will see that it was some kind of accident or jumping from a field to another field. So when I started my group, or just before, I was kind of associate professor or CNRS associate professor, working with Professor Jean-Marie Lane, who had been my boss for 10 years before or so. And we were very much interested in a big project, which was the photochemical cleavage of water to H2 and 1/2 O2. So you know that this is, of course, still a very active research field related to solar energy conversion to chemical energy, to making a fuel, because H2 is basically the ideal fuel. So we did some work which seemed to work, which was also very well greeted by the community. And like all the other people working in this field at the time, the main hero was Ruthenium Freezeback. So Ruthenium Freezeback, you've probably heard of it. It's a fantastic complex which has great photochemical properties. Its excited state is at the same time a very strong oxidant and a very strong reductant. So this is ideal if you want to split the water molecule, namely oxidize it to O2 and reduce it to H2. So there were probably thousands of publications based on ruthenium trisbipyridine and its properties. But, and there is a big but, ruthenium is a noble metal. As if you remember your classification, periodic classification, ruthenium is just below iron. And it's a noble metal, which means that it is very expensive, very rare, something like platinum or gold or rhodium. And so, in a way, there is basically no practical future for a molecule which contains a noble metal at the center. And thus, we decided, in association with a friend, an American friend, David Macmillan, to try and look for other possibilities than ruthenium. And we embarked in a big project on trying to use copper, which is basically free compared to ruthenium, in order to make and study inorganic photosensitizers. And this is what we did. And the very good news was that David Macmillan decided to take his sabbatical leave, coming from Indiana in the US, in Strasbourg. And so it was ideal for us. We started to collaborate from the very beginning when he was here. And we had lots of discussions. My group, all the members of my small group, they were discussing with him. And we ended up with a common project. So we had made this molecule for other purposes related to catalysis. And Dave Macmillan, when he saw the molecule, he got very excited. And he told us, we have to collaborate. You will make the complex, the copper-1 complex, and we will do all the photochemistry and all the photophysics on this molecule and let's say on the family of molecules which you will prepare. And we were, of course, very enthusiastic. And it worked beautifully. So we published a couple of papers on photophysics, photochemistry, but there was something else. And probably the something else is more important. Now look at this molecule. It contains two such ligands, which are kind of intertwined with each other. And if you look carefully, even more, if you draw the molecule, which was my duty, I had to draw the molecules before we published. And if you draw the molecule, you will realize that it has some potential in another field. Now let's materialize the endpoints of these ligands. So here, the two blue dots here correspond to the two endpoints of these fragments. And now let's do that for the other ligands. This ligand here has two endpoints, which I have now spotted as the red dots. it's clear if you look at it carefully, if you are able to interlink the two blue points and separately interconnect the two red points, you make a catenane. Very, very simple. So you make a catenane on paper, of course, and we thought, well, we are not at all experts in the field of catenanes. We feel very comfortable in inorganic photochemistry, catalysis, electrocatalysis, but we think, it could be a great idea for making catenanes very easily. And thus, after some discussions, we decided to start in the field of catenanes. And it was very, very fast. At the time, I had a very good friend, Christian Dietrich Büchecker, who was a CNRS researcher in another group, and she wanted to see something else. I think she was tired of what she was doing in that first group, and she wanted to explore other horizons. And she came to me and she offered to work in our, of course, I was very, very happy. I knew her extremely well, and I knew she was a fantastic organic chemist. And so together, just her and me, we embarked in this project, and within 10 months, we had our first publication on the making of a catenane. So this is written in French here, but I'm sure if you speak English, it's a new family of molecules, metallocatenanes, you can easily understand. So that was the very beginning. It was published many years ago. And I think all of a sudden it changed completely the scene. We demonstrated that within a few steps, 3 or 4 steps, you can make catenanes and you can even make grams of catenanes. So a student of mine, a former student of mine, made some video. And so this is the video. Now we start from this molecule here. The 2 OHs are represented here, 2 phenolic function, and we will mix with copper. So we take 2 such molecules, copper, and then we will cyclize on the right, cyclize on the left. It's a one-pot reaction, and finally we obtain the catenane. So it's a one-pot reaction to make the copper complex and then to cyclize, doubly cyclize. We have another strategy, which was also very useful, a little bit more complex. I think we have 2 or 3 additional steps, because first we have to prepare the ring, which is represented here. And then we will proceed to the gathering and threading reaction. We start from the ring, we add copper, we thread something, and finally we cyclize. And this allows us to make asymmetric catenanes, to have, let's say, a very large ring here, a shorter ring here. And so we made a family, very rich family of catenanes and rotaxanes based on this principle. So just now to summarize, we could make this compound in 3 steps, or 4 steps, or 5 steps, if you prefer to do it using the gathering and threading strategy. You can demetallate using potassium cyanide. You obtain quantitatively the metal-free species, and you can remetallate very easily by adding copper. We were lucky enough to have the X-ray structures of both species. So here we have the copper complex catenane, and after treatment with potassium cyanide, we have the metal-free molecule, which has a totally different shape. Here you have something which is compact and globular. Here you have something which is very flexible. Each ring can glide almost freely within the other ring. So totally different molecules. So we are still not yet in the field of molecular machines, but we noticed, we insisted in the first paper that the molecule undergoes a complete metamorphosis, complete change. So briefly, let me pay homage to the Catenanes people, to the groups which were interested in Catenanes and that one can consider as pioneers. I mentioned Ed Wasserman before. I also mentioned Gottfried Schill and Ludwig Haus, who published this beautiful synthesis, but exceedingly difficult and difficult to reproduce in '64. We published our first synthesis in '83. And from that moment, several groups became interested. My good friend Fraser Stoddart and his co-workers, they published their first Catenane in '89. And I think from that moment, let's say the field became more and more active. And nowadays, as you probably know, there are hundreds and if not thousands of new Catenanes which have been made by a very large number of groups. Just to tell you that for some time, we were not so much interested in molecular machines. We were interested in topology, in making molecules whose topology was too complex for a chemist to make them previously. So they were basically new species and very exciting from an let's say, organic chemistry viewpoint, but also perhaps physical chemistry viewpoint. And they were a challenge, simply. So we made this at the end of the '80s. We made the Trifold Nut at the beginning of the '90s, and we have been working on that for probably 10, 12 years. And we made more and more complex species. Let me talk of the Trifold Nut, because that is probably the molecule we are the most proud of to be able to make a knotted ring. Again, the people had discussed knotted molecules, but nothing had been done. And so we decided that it was time for us to make a knot based on the same strategy or something close to the strategy we had been using for making the first Catenane. So the strategy is described here, very simple. So this is what we have seen before for making a Catenane, a two Catenane. Now we will just multiply the complexity by a factor of 2. We start from a molecular string which contains 2 coordinating fragments, one here and the other here. And we will mix with 2 copper-1 ions to generate such a species. Very similar to that, but it's the dimer. And if we have a double-stranded helix of this type, we can cyclize and make such a compound. So by cyclizing, going from here to here, and separately from here to here. And if you look carefully, it's a ring. It's a single ring, and not at all a system containing 2 rings. So we have now a ring, and it's a knotted ring. If you remove the coppers, we obtain this species, which is topologically speaking, exactly the same as that one. So we embarked in this project again, and Christian Dietrich, she was incredibly good, but it took her 3 years of failure, I should say, before she could obtain the first knotted molecule. But she was doing also other things, so she didn't spend 3 years without any data, but she was also doing some other research. So this is now the reaction. We start from this compound. We have a CH2-4 linker between 2 phenanthrolenes, and this can be made at the 10-gram scale within a few weeks or so, or 2 weeks or 3 weeks. And now we will mix this with copper 1+. And we hoped to obtain this species. And yes, it worked. As I said, after several trials and attempts. And this is exactly what we wanted to make. Now we will cyclize, go from here to here, and separately from here to here, using the same Williamson reaction, ether forming Williamson reaction, based on cesium carbonate, which is the ideal base. And it worked. Finally, it worked. So cesium carbonate in DMF at 60 degrees, and a very long linker, the diiodo derivative of hexaethylene glycol, because you need a long fragment to go from here to here, to go from here to here. And finally, we obtain a poor yield of this species, the first molecular poor yield, but still we could make maybe 60, 50, or 70 milligrams. And with 70 milligrams, you can do all the studies you want to do. And so we could crystallize the molecule, and it was exactly as we had expected. This is the E3 structure. And if you want to convince yourself that we made a knot, you can start from here and travel all along the curve. So you will cross over, cross under, cross over, continue, cross under, cross over, cross under, continue. And you are back at the starting point. So you have 3 crossings. It's a single closed curve. No doubt it's a knot. Maybe you can see better on the, if I move the system and the animation. And so that worked very nicely. And I should say that from that moment, we made many knots, and they showed very different properties depending on the size, depending on the template. We used iron 2 or copper. And so we, in a way, we made a whole family of molecules with quite exciting properties. And I will just show you one example of something I think is an exciting property. We start from the dicopper nut, which we have seen before. Now we can easily demetallate using cyanide, because cyanide, as you know, binds avidly to copper, and copper cyanide precipitates out, and you obtain the free ligand. So this is the free ligand we obtained. It undergoes some kind of snake-like reptation. It's not very mobile, and we never had very beautiful NMR spectra because it is slowly gliding, slowly reptating. But the result is totally different if we take potassium cyanide. And maybe you can understand why. As you know, potassium, K+, likes to interact with crown ethers. Crown ethers, I'm sure that you have probably courses on crown ethers or cryptanes and cryptates. Potassium, K+, likes to interact with OCH2, CH2O, CH2, CH2O fragments. And that was totally unexpected. But if you have potassium cyanide, the cyanide will remove the copper, and the potassium will interact with the polyoxyethylene fragments so as to generate a new species. And in fact, we obtain also a double helical component here at the center with 2 potassium ions. But of course, the fragments are not the same. The coordinating fragments, they are OCH2, CH2O fragments. So I think the beauty of the process is that you start from something which is relatively hydrophilic because of those OCH2O fragments, and the center is hydrophobic, but you demetallate, you replace copper for K+, you generate a totally different molecule, which is hydrophobic at its periphery, and of course, hydrophilic in the center. So this is summarized here. If you look again, the same structure with copper. And if you replace it for potassium, you have now a totally inverted structure. And as far as I know, there are not so many examples in the literature of complete inversion of a molecule by just coordination chemistry. Now I have spoken about catenanes and nuts some time. And at the very beginning, some people were laughing at us, and they were some other people were interested in our work, but some others were telling us, well, catenanes, nuts, they do not even exist in nature. Why are you working in this field? And in fact, catenanes and nuts are very common in biology. When I say very common, it means they are everywhere. And just to show you, DNA, circular duplex DNA in the plasmid, it forms catenanes and nuts all the time when it recombines or when it replicates. And you have here a couple of beautiful examples of electron micrographs of the Trifold Nut using DNA. Of course, the length, the length scale is not the same as for a molecule, a classical molecule. We are rather in the micron range, but this is very common. I mean, DNA forms nuts and catenanes. I just selected a beautiful example of the figure 8 catenane made out of DNA again. And this is a mythic figure, the Whitehead link, a 5-crossing catenane. And so DNA made that billion years ago. Maybe something you are not aware of. If you look at Cambridge Databank, X-ray crystallography databank, some people have done that, and they could identify knotted proteins. And roughly there is 1%, even a little bit more than 1% of all the proteins known in terms of structure, which are knotted, which are Trifold nuts. So Trifold nuts are very common in biology because 1% of the proteins are knotted. And the last example is absolutely spectacular. More than 20 years ago, there was a beautiful piece of work which was published in Science by this group of people, biologists and crystallographers, and they crystallized a virus. So that was already relatively classical. So many viruses have been crystallized and studied by X-ray structure. But this one is very special. So if you look at the envelope of the membrane, you can use both terms, of the virus, it's a very thin envelope, 18 angstroms, because it consists of proteins, like many viruses. And this virus has something special. If you look more in detail, and this is what the people did, they observed that on the membrane here, you have proteins, cyclic arrays of proteins, which are interlocking with one another. So you can identify a pentagon here, hexagon here, hexagon, pentagon, etc. And so you have something which is a chainmail. It's a natural chainmail. A chainmail, this is something that the knights were wearing to protect their bodies when they were fighting their enemies with big swords. And the chainmail is fantastic because you can still move, you are protected, but for the virus, it's very nice. It can pass barriers, distort, and find the bacteria which it wants to invade. So this is one of the most beautiful examples of a topologically non-trivial molecule in biology. Now, let's look at what some other people have done, because rapidly, some other groups were interested in nuts and catenanes. And I will just show you some spectacular examples. And again, I insist this is not the work we have done in Strasbourg. This is the work done by other people. And I thought that you should be interested in that. So in 2004, there was a fantastic piece of work published in Science by Fraser Stoddart and his co-workers, Cantrell, who I think is still editor of Nature Chemistry, Chit-Chat, and some other people I met, and the crystallographer Atwood, and they could make the Bohomian rings. And I think it's a real tour de force, to make the Bohomian rings with molecules. The Bohomian rings, if you look carefully, if you isolate by your mind 2 rings, you will observe that they are not interlocking with one another. Let's take the red ring here. It sits above the green ring. The blue ring here sits above the red ring. And so this is true for the 3 of those rings. They are not interlocking with one another, but if you have the system, thanks to the 3rd ring, it's an interlocking ring system. And so this is also part of nut theory. It is identified. And it's a symbol. This is the symbol of the Bohomian family in Italy. The Bohomian family, which was a very powerful family in the Middle Ages. They had the Pope even. And I think it is fantastic that molecular chemists could make the Bohomian rings at the nano level using molecules. The pentafoil nut is also a very impressive piece of work, started by David Lee and his group at Manchester. I'm not sure he was at Manchester at the time, maybe he was in Scotland. But so the Trifold Nut is also a very exciting object. And so the strategy they use is really nice, very clever. It is partly based on some previous work done by Professor Lane and his group, but significantly different for everybody to say that this is David Lee's work, clearly. So you take a fragment of this time. You have here a bipyridine. A bipyridine is potentially, it's a chelating. And here you have a pyridine and an aldehyde. And if you have some primary amine around, the aldehyde and the amine can react with one another, and you will generate a sheaf base or an imine. I used to call that a sheaf base. So a C double bond. And then you will generate a chelating group here as well. Now, let's take that. We have the connector here, which will be able to bind to the aldehyde and to form a sheaf base, and at the same time, a chelating group. So you mix, you take this fragment, you take this other fragment, and you take iron 2. It is essential to take a fragment which is very, very flexible. If you take a polymethylene fragment, it doesn't work because this is very rigid, no flexibility. Here you have flexibility. And what you will obtain at first is a system of this type. So the iron 2 centers, they want to be hexacoordinated. So they want to surround themselves with 3 bidentate chelating groups. So you have already one here, and then some others, which will come from the other fragments which are around here. And so you have 5 fragments, let's say, and 5 iron 2. And finally, you will generate this species. Well, it looks kind of black magic, so to say, but it makes sense if you think of it for some time. I'm sorry to say that we haven't got the time to enter all the details, You can also read a paper which was published already some time ago, 10 years ago, but they could make the pentafoil nut totally convincing. Now, perhaps even more impressive is the work on the 7 crossing nut, which is called the endless nut. It's a symbol in the Celtic art, very important symbol. 7, 4. 7 means that you have 7 crossings, and 4 is related to the dimension of the space in which you can embed the nut. So normally you should argue, because here you have more than 7 crossings, you have 9 crossings. But those 2 crossings do not count, because if you turn this part, and if you turn this other part by 180 degrees, you will completely erase the crossing. So it's indeed a 7 crossing nut. But this is the way the artists like to represent it. Now, I'm pretty sure you will see exactly the strategy that they have proposed. You start from something which contains 3 tridentate coordinating fragments. Here, 1, 2, 3 nitrogen atoms. It's a terdentate system, like terpyridine. Here, the same terpyridine, very similar to terpyridine. And finally, here again, the same 3 nitrogen containing system, which is again close to a terpyridine. So let's represent it like that. On top of that, we have some other functions. So 1 metal, 2 metal, 3 metal will be able to interact with this fragment. Now you have this fragment, and when you mix, I'll go back to that, you mix with iron 2 and or zinc 2, but iron 2 is more useful. And then what you will obtain is this species, as I said, this species. And basically you have no other choice. So you have here 1, 2, 3 metals, 1, 2, 3 additional metals, and 1, 2, 3, the 3 last metals. So it's a 9 transition metal system, and it's a 9 molecular, no, it's a 6 molecular components, organic component system, which can be represented like that. So you have 1, 2, 3 organic strings or rods, if you like, and 1, 2, 3 organic rods, and they are crossing. It's kind of inter crossing, and so you have this system, and you can do metaphysics, because I should have mentioned here you have double bonds, and those double bonds are ready to undergo metaphysics. So using Bob Grubb's strategy, you will do a metaphysis, ring closing metaphysis. And so you will do ring closing metaphysis from here to here. You will do ring closing metaphysis from here to here, etc. From here to here, from here to here, from here to here. The most important ones being the 4 ring closing metaphysis, which are here, 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 and here. And of course, the 4 others are important, but let's say they are very easy to perform because the 2 organic groups are close to one another. And so it works beautifully. They could make the 7 crossing nut, the endless nut, and then I think perhaps one of the remarkable features is that they could crystallize the system. And David Lee was kind enough to send me all the data and those beautiful videos. And you can visualize the system, 9 metals, and this kind of rope here. And this is the X-ray structure. And thus, there is no doubt that they could make a 7-crossing system. So let me now finish up based on somewhat similar work. Now they will be perhaps even more ambitious. They will try to move on towards applications, potential applications. And so they will do some kind of woven fabric using molecules. So we start from basically the same system, except that there are no alkenes as terminal functions here, but we have thiols, a short chain and thiols. And thiols will be easily oxidized to disulfides, which will lead to bridging molecules, to connecting molecules to one another. And so here they have a video, which is, I think we have to be very careful with videos. You know, videos can be misleading. One shouldn't believe exactly what you see on the video, but I think it makes sense to believe that maybe there is something similar to what is shown on the video. So first, they will make the precursor, as I said before. So they will add iron and perchlorate. So this is what you will obtain. And now they start, so this is the starting molecule. And now they start to oxidize and to make disulfide bridges. It makes sense. Although, as I said, it's an idealized view of the process. And once they have done that, they can remove what they want to remove, the metals and the perchlorates. Everybody goes out together, that's it. And finally, now they have some kind of fabric, a woven fabric. Again, this is some idealized view. And this is what they obtain now. Practically, they obtain this kind of fabric, which is, of course, less nice than what we have seen on the video. So let me finish up by thanking the people who have done the work for the first part of my lecture, which was the work done in Strasbourg in my group. The French system is such that we can work as groups of people. I don't know in Ukraine if you have something similar, but thanks to the CNRS and thanks to the way the university is organized, we can work as groups of professional people. And when I started my group, we were 4 or 5 permanent people who gathered. We were more or less all the same age. And this is very nice for the students because they have, in a way, 4 or 5 supervisors, and they can ask somebody, who is not the super boss, who might be traveling, but they can ask somebody who is highly experienced for advice, and so the students like it. And so here are the names of the people who are working with me in my group as permanent people, professors or CNRS professors, and PhD students. And I just would like to mention that Sasha Prikotko was a fantastic Ukrainian postdoc who did some beautiful work recently, much more recently than what I spoke about with octahedral coordination. And so he's a fantastic guy. I think he's now in Germany, unfortunately for your country. So here are the people who did the work on molecular machines, but I will talk about that on Friday and the same year. Let me finish up by thanking my university, the French CNRS, the European communities, and I believe Ukraine has access to European money, which is very good. My new institute, because I had to retire from the CNRS when I was at Institute of Chemistry, and I was invited by ISIS, the fantastic institute founded by Jean-Marie Laine, and I was also invited to join Northwestern University, which I did. I spent 3 years part-time there. It was a great experience. And let me thank Jean-Marie Laine, Malcolm Green, who very unfortunately passed away 2 years ago, a great organometallic chemist with whom I got introduced to inorganic and organometallic chemistry, to teachers, my family, and my 2 Nobel Prize friends, Fraser Stoddart and Ben Feringa. And finally, thank you so much for your attention. Thank you.
Thank you very much for your impressive lecture and complicated chemistry.
Yeah. Sorry, yes.
Exactly, complicated notes. Yes, dear colleagues, do you have any questions to our speaker? Please don't hesitate to ask.
Valentin, I have a question.
Professor Kalchenko, please.
Oh, thank you. Jean-Pierre, fantastic lecture. I have a question addressed to chirality.
Yeah.
You synthesize and show us Trifold Nut and complexes. These molecules are chiral, yeah, or not?
Yes, you're absolutely right. This is a great point. Yes.
Chiral. In principle, it's possible to obtain 2 stereoisomers, or not?
Yeah, we could.
This is just theoretical question.
No, it's a very important point. Thank you for the question. If you look at this molecule, it has a right-handed helix. If it is the right-handed helix here, it's a right-handed nut. And of course, you know, I should have mentioned, we made the mixture, we made the diastereomers, not one enantiomer. But having made this compound, and I should show you that, having made this compound, we could separate, we could isolate both enantiomers by crystallizing the molecule. It's a dication with binaphthyl phosphate. Binaphthyl phosphate, you know, optically pure, will lead to diastereoisomers, and one of the diastereoisomers crystallizes out and the other stays in solution. But I had no time to discuss that, of course. It would be another lecture.
Thank you very much.
Thank you. Other questions?
I have a question, please.
Yes.
So my question is, as far as I understood, formation of knots is facilitated somehow by introducing metal ions into the construction of smaller molecules. Yeah. What is the prerequisite for the formation of such knotted structures in biopolymers like proteins and probably DNAs? Ions are necessary, or it is possible to form such knotted structures by other type of interactions within molecule?
Yeah, that's a very good point. I think, you know, no doubt that hydrogen bonding replaces transition metals. If you have the appropriate hydrogen bonding, you can basically control exactly the geometry of the system be it with proteins or RNA. Hydrogen bonding plays an essential role. And just to go a little bit further, several groups have made synthetic groups, purely synthetic chemists, made nuts and catenanes, very beautiful, very complex ones, using hydrogen bonding as templating principle, because you need some templates. Yeah. I do not hear you anymore.
Thank you very much. Sorry. Thanks.
No problem. Thank you.
Thank you for a question and for answer. So, dear colleagues, more questions to our speaker? Yes, Professor Komarov, please.
Yes, thank you very much. I have a question. Professor Sauvage, is there any ideas how the knots are formed in nature from DNA, etc., etc.? Is there any metals involved or whatever? That's the question. Thank you very much.
Honestly, personally, I do not know. I will be very honest. I do not know.
Oh, yeah.
I'm not sure. I'm not sure that our biologist friends have a deep knowledge about that. I don't think so, but I might be wrong. Again, I mean, my guess is that hydrogen bonding plays a very important role. But
Yeah,
maybe
perhaps.
zinc, magnesium, which is around, can also play some role, no doubt. But personally, I will be honest. I don't know. I'm sorry.
Thank you very much for the answer and the fantastic lecture. Thank you very much.
By the way, I had the same question because it's very interesting how the nature makes these molecules.
Yes.
With a mechanism of, okay, we know about, by the way, about the synthesis, what about purification and isolation of such complicated molecules? And what about yields?
Yeah, some of the yields can be extremely good. If I take the catenane, catenane. And so at some stage, we decided to use a ring closing metathesis as the key reaction to finish up the work, to make the catenane. And the yields were classically in the 90–95% range.
Oh, rather good.
For the lab step. And for the nuts, using ring closing metathesis, it was, let's say, the most difficult step, which is the cyclization, making the ring, was, I think the record was 75%. So surprisingly good, so to say. And the molecules are treated exactly like organic molecules. We chromatograph them on silica using dichloromethane, mostly dichloromethane with a trace of methanol, or very classical organic molecules.
Nice.
Yeah.
Thank you. So, more questions for today's lecture? I don't see. Okay. Thanks again for your very nice presentation and impressive lecture. And I would like to remind that the next lecture of our speaker will be the day after tomorrow, and concerning molecular machines. Yes?
Yeah.
Yeah, okay. Thank you again.
Thank you, Valentin. Thank you.
Have a nice day.
Yeah, you too. See you on Friday.
See you Friday.
Okay. Bye.
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 Thank you very much. Thank you very much. Bye.